Hello children. We are going to see a very important chapter in our 11th standard chemistry as atomic structure, and in that we will see a very important topic called quantum numbers. Now children, when you think about quantum numbers, the very important concept which is required to understand quantum numbers is electromagnetic radiation. Now this electromagnetic radiation was taken in terms of wave nature by Maxwell in the year 1870. In the year 1900, Max Planck taken the particle nature of electromagnetic radiation. Now, in the year 1924, de Broglie was a scientist who combined both Max Planck and Maxwell ideas of particle and wave nature, and he gave his own theory. He said that all moving particles, be microscopic or macroscopic, have both wave and particle-like nature. In the year 1926, Schrödinger was the person who combined the ideas of all these scientists and said that electrons also have wave and particle-like nature. He again gave a theory which we call as wave theory, wave mechanical model or quantum mechanical model. In order to explain the three-dimensional behavior of electron in the electronic field of the positively charged nucleus, he gave an equation that we call as Schrödinger wave equation. Now he found that this equation has many possible solutions, but he collectively gave only few possible solutions, few meaningful solutions, which we call them as quantum numbers. Now what are those meaningful solutions and what were those numbers? Let us see one by one. The first and very important quantum number was principal quantum number, which is denoted by a small letter n. The second quantum number was azimuthal or subsidiary or angular quantum number, which we call or which we denote by small letter l. And the last very important quantum number was magnetic quantum number, that we denote by ml. Now children, let us try to understand the very important quantum number, the principal quantum number. Now basically children, this quantum number gives the energy level of the electron, the energy level in which the electron is present. So in a way we can say that it actually gives the size of an atom. This quantum number has all the integral values from 1 to n. And using this quantum number we can also calculate the number of electrons present in a particular shell using the formula 2n square. Fine? That's right. Okay, so as you can see here that number of electrons in a particular shell can be calculated using the formula 2n square. So we have to just substitute the value of n and we have to get the numbers as 2, then 2 into 2 square as 8 and 2 into 3 square as 18 and so on. Now this quantum number also helps us to calculate the energy of hydrogen or hydrogen-like species. Now what do you mean by hydrogen-like species? Hydrogen-like species like He+, like Li2+, etc. So especially we are talking about all monoelectronic systems or the species containing only one electron. Now children, for multi-electron system, this quantum number gives only the values which are probable values. Fine? Okay children, now let us try to understand the second quantum number as azimuthal quantum number, which we also call as subsidiary quantum number or angular quantum number, and it is denoted by the small letter l. Now children, all the electrons which have the same value of n cannot have the same energy, and this was verified with the help of this quantum number. Now with this quantum number we can also say that electrons have sub-energy levels. Now this quantum number has values ranging from 0 to n minus 1. So we can say like one value less than principal quantum number. Let's write the values. Now children, let us see the next quantum number as azimuthal quantum number or subsidiary quantum number or angular quantum number. Now, all the electrons with the same value of n, that is principal quantum number, cannot have the same energy. Now this verification is done with the help of this azimuthal quantum number. Azimuthal quantum number has all possible values from 0 to n minus 1. Now, for every value of n, the principal quantum number, L also has its own values. Let's try to see one by one. Okay, now for n is equal to 1, L is equal to 0. So what I told you, that the value of L will be 1 less than the principal quantum number. Similarly, for n is equal to 2, L will be 1, n is equal to 3, L will be 2. Now children, for every value of L, there is a notation that we call as orbitals. Now what are the notations? When L is equal to 0, the notation is S, or we call as S orbital. When L is equal to 1, the notation is P, that we call as P orbital. And when L is equal to 2, we call as D orbital. Now children, I am talking about the term orbital here, and orbitals basically represent the sub-energy levels. Now, this angular momentum or angular quantum number generally help us to understand the shape of orbitals. After this, let's try to understand the third quantum number, that is magnetic quantum number. In order to understand this magnetic quantum number, we need to understand a source which produces spectra. Now, whenever a source which is able to produce spectra is placed in a magnetic field, it is found that the spectral lines are split into fine patterns. Now, it is also found that in case of electrons, when they move around the nucleus, they produce electric field. And when this electric field comes in alignment with the magnetic field of the Earth, these electrons orient themselves in different fashion. Now these specific orientations of the electrons around the nucleus result into different orbitals. Now let's try to understand that how this magnetic quantum number help us to understand the different orbitals, the different types of orbitals. Now children, as you can see here, that it is denoted by the letter ML. This L over here shows its relation with the previous quantum number, that is azimuthal quantum number. So the values of magnetic quantum number are represented using the azimuthal quantum number. The possible values that this magnetic quantum number can take are ranging from minus L to 0 to plus L. So in total, we get 2L plus 1 values. Now let us see how its relation with azimuthal quantum number can give us some insight into different types of orbitals. First example here. If L is equal to 0, what can be the possible value of ML? We can expect only one value, right? So, when L is equal to 0, the orbital was S orbital, and for S orbital, the magnetic quantum number will have only one value, that is 0. Let's go for the second value. If L is equal to 1, what do we write for ML? We can write as minus 1 to 0 to plus 1. So in total, there will be 3 values. And children, these 3 values actually denote the 3 different orientation for p orbital. Why? Because L is equal to 1 denotes p orbital. Now let's try to understand that how these 3 orientations are related to different types of p orbitals. By convention, when you just look at these values, minus 1, 0, plus 1, by convention, this plus 1 is assigned to a suborbital called PS. Similarly, 0 to PZ and minus 1 to Py. So this convention we have to keep in mind. After this, let's see what happens when L is equal to 2. Okay, now let us see what happens when L is equal to 2. For L is equal to 2, ML can have values as minus 1, minus 2, minus 1, 0, plus 1 and plus 2. So in total we got 5 values. Now let us see how these 5 values are assigned to different types of d orbitals. Now look at the values and look at the different types of d orbitals. When you just see dx square y square, plus 2 is conventionally assigned to the orbital dx square y square. Plus 1 is assigned to dxz. 0 is assigned to dz square. Minus 1 is assigned to dyz. And minus 2 is assigned to dxy. Now children, in order to define an electron, the position of an electron in an atom completely, scientists felt the need of one more quantum number. And this quantum number was called as spin quantum number. Now, electrons, when they revolve around the nucleus, they revolve around their own axis. And this movement of the electrons around their own axis result into spin movement. This spin movement of the electrons can be either clockwise or it can be either anti-clockwise. In order to account for these two spin movements of the electron, scientists suggested the two values, the two possible values of spin quantum number as ms is equal to plus half and ms is equal to minus half. Plus half to account for the clockwise movement of the electron around its axis, and minus half for the anti-clockwise movement of the electrons around its axis. Okay children, I hope that you have understood all the 4 quantum numbers. Let's quickly revise all these quantum numbers. And what are quantum numbers? Basically, a set of 4 quantum numbers which completely define an electron in terms of its energy, orientation, shape and spin are called quantum numbers. Now let's quickly have some examples based on these quantum numbers. Number 1, we have 3px. Now when you just look at this configuration and try to find out the different quantum numbers, we can have a simple formula. And that simple formula is n L raised to x. When you just look at the formula, the n over there, the letter n represent principal quantum number, L represent azimuthal quantum number, and x over here represent the number of electrons. So it's very easy to calculate the number of quantum numbers. For 3px, when you just compare this configuration with n L raised to x, you can easily find out that n is 3, p over here, so px, that's the p orbital, will have L is equal to 1. And children, when you just look at this p orbital in the form of px, by convention, px orbital has been assigned plus 1 in terms of magnetic quantum number. So the 3 quantum numbers for the configuration 3px are n equal to 3, L equal to 1 and ml is equal to plus 1. Now let's take another example wherein we have an electron as well, as 2py1. Again, try to compare this 2py with n L raised to x. What we find? For 2, we can write n is equal to 2. And again, it is a p orbital. For p orbital, L will be 1. And again, when you look at this py, by convention, py has been assigned ml value as minus 1. And now children, look at this number here, 1. It means that 2py orbital has got 1 electron. And by convention, if you just have only 1 electron in a particular orbital, it is assigned plus half. So the spin quantum number value for the sole electron will be plus half. So different possible values, different quantum numbers for this configuration 2py1 will be n equal to 2, l is equal to 1, ml is equal to minus 1, and ms equal to plus half. Clear? Thank you very much. I hope you understood all the quantum numbers.